Okay, so we're talking about analytical techniques and analysis of organic compounds. So the goal of those analytical techniques is to identify the structure of organic molecules. And of course, organic molecules, we know that they have a specific a structure that it's really important, but not only we need to determine the type of functional group. So there are different analyses that we could do. From previous years, we saw the infrared spectroscopy that was used to identify the type of bonds, or better, the functional group present in a molecule, functional group. Of course, it's quite limited, but at least we know which functional group is present, which we could identify also by doing some like test tube analysis. But of course, the infrared is an analytical technique, so it's quite simple to run. And then we had the mass spectrometry. So the mass spectrometry, it was useful to identify the MR of a compound by looking at the heaviest peak. So this was the molecular ion, just to refresh a little bit. It gives the MR of the compound. It gives us some structural information, but it is quite limited because it depends a bit on how the molecule fragments due to ionization. So all of this comes from year 12 notes. Of course, those give some kind of information, but quite limited. The NMR, it's the analytical technique that gives a bit the most information. Okay, so it's a bit more complex of how it works, but it's a type of spectroscopy. And what this tells us is that it uses electromagnetic radiations, and it studies the interaction with the substance. Okay, and in this case, we're looking at the interaction between the we're using the interaction, or better, we're actually analyzing the nucleus of atoms. Yeah, just it's quite important to understand that we're talking about the nucleus of the atoms, okay, and not just like the vibration of the bond, just to distinguish it from the NMR. So the nucleus of each atom generates a magnetic field because it rotates, because it spins around. Okay, if an atom has an even number of nucleus, of particles in the nucleus, like carbon-12, overall it doesn't have a spin because they all cancel out. In fact, in the NMR, we can analyze only elements that have an odd number of particles in the nucleus, which overall they would have a spin, because these spins generate a magnetic field. The direction of the magnetic field depends in which way the nucleus is, which way around it turns. Okay, and normally there are two different ways it can spin up or spin down. And because it generates a magnetic field, it can also interact with the magnetic field, which means that basically the nucleus can spin or can align, or the spin of the nucleus can align. Let's say this is energy. It can align with or against the magnetic field. Okay, so let's say that here we have a spin, for example, like this. Here it can align with or against the magnetic field. So the arrow don't really represent anything, just the direction of the spin. And this difference in energy is what we can measure when this magnetic, well, actually it's the energy gap. It's the energy used to rotate the spin of the nucleus, and it uses radio waves. So the radio waves cause the nucleus to change in spin. This is because when the magnetic field is applied, the nucleus can align with or against the magnetic field. But when energy is applied, specifically a specific frequency of radio waves is applied, it would cause the spin of the nucleus to change. So the point being is that we use the radio waves. That's why it's a type of spectroscopy. We use radio waves, and we measure directly the nucleus. So a different type of nucleus would absorb a different amount of energy, okay, in order to change, this spin. And this is affected by many things, like, of course, the type of atom, like carbon-13 and hydrogen, they actually have a different sensitivity. So it's a very different frequency. But within the type of hydrogen atoms, the environment in which they are, and as well as the carbon, depending on the neighboring atoms and whatever shield the nucleus, it would have an effect on this amount of energy. And therefore, we can detect it in some kind of spectrum. Okay, so when we talk about the NMR, the very important things to that we can identify from a spectrum, they are 4. 1, the number of peaks that are present. It tells us the number of chemical environments that are present. So chemical environment. What does that tell us? Well, it tells us about the symmetry of the molecule. If the molecule is very symmetrical, it would give fewer peaks. Okay, so it gives an idea about the symmetry, because we always have to remember that the point of this NMR is to actually find the structure of a molecule. Okay, so the environment is represented by the number of peaks. Okay, the chemical shift. So this is how far is from a reference point. It tells us about how close. Actually tells us about the type of bond, let's say. Type of bond, in the sense that in a structural point of view, it's the how close or far is from an electronegative atom. And we will see why. But remember, we are detecting the nucleus and the spin of the nucleus, and the energy required to change that spin. Okay, so different nucleus, different amount of energy. Yeah, and it would be in a different position of the spectrum. Okay. There is one other thing that's a bit more complex, the splitting pattern. And the splitting pattern tells us basically the splitting pattern means that one peak, it's split into a specific shape or a specific type of peak. And that would tell us the number of neighboring hydrogen. Okay. So the splitting pattern tells us the number of neighboring hydrogen, because the proximity to other nuclei that have a magnetic field will affect the interaction of the magnetic field, the interaction with the magnetic field of the nucleus that we are referring to. Everything will come together, just to see a bit that there are at the end 4 things that we will consider. And the last one is the integration, calculated as the area under the peak, which tells us the number of hydrogen that are responsible for that peak. There are a lot of things that will come together to give really, really useful structural information. And those are the things that we will consider, or better, we can identify for hydrogen NMR. For carbon NMR, carbon-13 NMR, we will consider only the chemical shift, the number of peaks. Okay. And then the integration number as well. Actually, it's just the splitting pattern that we want to consider. Okay. The reason is that the carbon-13, it has a much lower abundance compared to the hydrogen, which means that it's not, the NMR is not sensitive enough to detect that splitting. Okay, but that's what makes it a bit simpler, I think, and the hydrogen NMR is a bit more complex to interpret. Okay, just a few things to consider. The NMR would look something like this. We have something that is 0. It's called reference point. 0 what? 0 part per million. And this tells us how far a signal would be from the reference. So how different is from the reference. Okay. And the reference point, it's TMS, or very calibrated spectrum, we can say. And it's called the tetramethyl silane. And it has some specific characteristics for that to be the reference point. But here is the peak corresponding to TMS. TMS, tetramethyl silane, it looks like this. And after we understand each of the things, each of these like 4 things that we need to identify, also will make sense why TMS it's such a good reference. But how far it is from the TMS, it will tell us how different the type of hydrogens that are detected are, and this gives an idea of the molecule and the structure, considering also all the other things like the splitting pattern and so on. Another thing to consider, we're talking about detecting hydrogen, not carbon. In this case, we're talking about hydrogen NMR, but this means that hydrogen NMR is present in pretty much all of the organic molecules. Yeah, which means that the samples, they have to be dissolved in solvent-free hydrogens. So the solvent, to remember, there could be D3Cl or D2O for polar molecules. This or CCl4 could be a good one as well. Anything that doesn't have hydrogen, yeah. But because D is deuterium, and deuterium has a mass number of 2, which means that it's not detected in the NMR. But those are called the deuterated solvent because they contain deuterium. Okay, and then we'll come back to this reference point. Going back to each of these analysis and what will appear on the spectrum, we said the first thing, the number of peaks will tell us the number of chemical environment. Okay, so let's focus on that environment. CH4, for example, we have a carbon with 4 hydrogens. All the hydrogens are bonded to the same carbon, and there is no other neighboring atom. So there's going to be one peak, one environment. Okay. C2H8. No, 6. C2H6. All of the hydrogens that are normally on the same carbon, yeah, the hydrogens that are on the same carbon, they will be considered chemical equivalent. Okay, because they are attached to the same carbon, they're attached to the same atom. But then we always need to analyze, okay, what about the neighbor? Yeah, and the neighbor, we look at the carbon, remembering that we detect hydrogen, not carbon in this case, because it's hydrogen NMR, but we need to think, okay, what neighbors do this CH3 has? Well, actually has another CH3 that they're exactly attached to another CH3, which means that they're all chemically equivalent. So even if it's a larger molecule, it has 2 different sets of hydrogen, it's still going to be one peak only. Yeah, and we can see it also by looking at the symmetry, because very symmetrical molecule, which means that those 2 groups will be the same. And when we do the interpretation, we will always look at like CH2, CH3s as just a whole one whole group, because it makes the analysis a bit easier, because we know that the hydrogens on the same carbon will be the same chemical environment. If we look at C3H8, okay, now maybe there is something different. and I'm going to write now as a CH3s because we said already they would be equivalent. Okay, but the focus now is on this CH2 group. So those CH3 are going to be equivalent because they have the same neighbor, that's CH2. But this CH2 is different from the CH3 because it's next to a CH3, while the CH3 is next to a CH2. So actually, we will have two different peaks here, even though we have, of course, more, like now, more atoms in the larger molecule. So to find the environment, we should look at the, we should look at some symmetry, and then we always needed to analyze, okay, so what environment, what is the neighbor? And that would cause it to be a different environment. Okay, so let's look at some other example. We could have slightly more complex molecule. Let's say now there is a CH3 group, a CH2, CHOH next to a CH3. Okay, so I hope it makes sense, the structural formula. In the worst case, we would, if we needed to analyze it a bit better, we would write the either displayed or the skeletal. So we can analyze each group. Now we don't look at each hydrogen singularly, but we analyze each group. So CH3 next to a CH2, CH2 to a CH3 and CH. The CH has attached a CH2 and a OH and a CH3. So actually there is no equivalent neighbor in this molecule, which means that each group of hydrogen will give a different peak. Yeah, this is tricky. Let's forget about it for now. Yeah, so we would have 4 different environments. So we expected to see 4 different peaks. Okay, so that's what the environment tells us. And so environment is about symmetry of the molecule, and we just need to look at each group of hydrogens and the neighbors that it has. So the first thing that we've considered is the number of peaks, number of chemical environment, information about the symmetry of the molecule. Chemical shift. The chemical shift tells us about the type of bond, so how close, how far it is from an electronegative atom. Let's try to understand why, first of all, an electronegative atom affects the position of the peak. And here it's useful to look at the at TMS, because it's all of these hydrogens, they are attached well to a carbon, attached to a silicon. So silicon is, let's call it electropositive, yeah, which means that in this case it's carbon that is more electronegative. Therefore, it gives a little bit of its electron density away to the silicon. But this means that the absolutely the other way around, because the silicon is electropositive, so carbon is more electronegative, takes electron density towards it. Okay, which means that the electron density of on the hydrogen is higher. And if you think about what we said, is that we are detecting the nucleus of the atom. If the nucleus is more shielded, so it has those shells of electrons, these clouds of electrons, then it would absorb less radio waves, but it would be less exposed to the nucleus, therefore less shifted, to think it in a simpler way. Okay, so the closer it is to an electronegative atom, the further away it will be. It would be shifted. Okay, so let's look at some examples, but that's the general idea. Okay, we can calculate the chemical shift because it's all compared to the field that is measured for TMS. In fact, we would basically calculate it as a difference between the field measured in TMS divided by the field for TMS times by 10 to the 6, so it's part per million. But it's basically just how much of the field is shifted from the field of TMS. Okay, and I think it's too relevant to know exactly what it means, but just why that happens. Okay, but the symbol for chemical shift is this one. okay, the small delta, and is a measure in parts per million, okay, and it's basically it's a part per million of how far the magnetic field required for absorption is shifted away from that of TMS. Okay. Over the complex, the thing to know is the more electronegative, with the more the electronegative group, the greater shift it gives. And the easy way to remember it is always that we know we're detecting the nucleus of hydrogen, the most electron density it has on it, the less shifted it will be because it's all shielded. But an electronegative atom would withdraw electron density towards itself, so would be shifted even more. Okay, and of course there are like specific parts per million or specific peaks. But another way to think about it is that, well, the closest it is to TMS, the more similar it is. Yeah. We can think it in that way. But let's think about couple of different examples. Let's say that we have here these carbon, let's say whatever molecule it is, doesn't matter. But we have this CH2 group attached to an OH. And then we have this CH2 group attached to a CH3. And then we have this CH2 group attached to a carbon atom. The one that is most shifted will be the one that is directly attached to the electronegative atom, because this electronegative atom is taking electron density away, it's going in this direction. So those hydrogen nuclei are more exposed, and therefore there will be more shift. I think that's the easiest way to remember it. So it will be the most shifted. The other one, the carbonyl, would also be a bit shifted because you can see there is a bond in between because there is a carbon now, it's not directly attached to an electronegative, but it would still be shifted because it is quite close to an electronegative atom that takes all of the electron density away towards itself. Hydrogen's more exposed. This CH2 is the one that is going to be the closest. So this is referring to TMS because it's next to a CH3. So it's not going to be so much different from these CH3s that don't really have any electronegative atoms attached. Okay. I think that's the easiest way to remember, and it gives that it's useful to then once we identify all the groups that are present, it's like, okay, so where are they in the molecule? Yeah. And that's relatively simple to understand, in my opinion. The more complex thing comes with the splitting pattern, okay? Because it's a bit like, okay, we're the splitting pattern, what does that mean? Let's just think about on these examples. And here we're looking at the third one, the splitting. And the splitting tells us about the neighbor. So let's say we have this molecule, we have CH3, and no, actually, let's do CH3. I'm just going to write the hydrogens like this to make it easier. And then we have carbon double bond O and OH, which means that we don't care so much about this part right now. Those hydrogens, they're next to other hydrogens, yeah, of just one bond difference. And this means that they are experiencing the magnetic field, yeah. They experience the magnetic field of neighboring hydrogens. Okay, let's think in a way. So the nucleus of this hydrogen can spin up and spin down, right? So these CH3 group can experience the field of the neighboring hydrogen as one is up and one is down, isn't it? Because they could be two opposite spin. But it could also experience some of this hydrogen having a spin in the same direction, aligned with the magnetic field, or could also experience the spin of hydrogens that are aligned in the same, but in the opposite direction. So overall, it looks like this CH3 group is experiencing 3 slightly different magnetic fields. And this would cause that single peak of the CH3 to be split into what it's called a triplet in this case. So this splitting pattern, this is called a spin-spin coupling. It's due to the the spins that are the spins that are, sorry, I just lost my screen. Where is it? Okay, the spin. Oh, and we're looking here. The spin, as you can see, that that is experiencing in the neighboring hydrogen. Okay. The ratio, the relative size of the peak is something that I wanted to mention, because just looking back at this diagram, we said that it experiences 3 slightly different magnetic fields, both down, both up, down and up, no, up and down, but they could also be down and up, which means that there is double the chance to experience the spin being basically different. And that's when it gives the size of the peak that is relevant with the ratio 1 to 2 to 1. It's a bit complex to explain exactly like all of this, because when we get now a bit bigger neighbors, there are more spins that can be experienced, and therefore the splitting gets bigger. But there is a very, very simple way to remember it, and is that the peak will be split to an n plus 1 number of atoms. Okay, so if we have, and I think this presentation was a quite nice summary to explain that spin-spin coupling. Oh no, what did I do? Sorry, I just lost the presentation. It's here. Okay, so if the neighbor it's a 0, if there are no neighboring hydrogen, then we can detect only the field of that hydrogen. So it will be just 1. If the neighbor is just 1, we will split it into a doublet. That's the name. And the easy way to remember is always that n plus 1 splitting pattern. 2 neighboring hydrogen splitting into 3. 3 neighboring into 4, and so on. And the ratio, it just tells us the probability of how it experienced the spin. So as we show from the diagram, up and down and down and up. Okay. So let's do an example. Now there are already a few things that we can detect. So let's say that we have CH3 attached to a CH2, attached to a carbonyl, attached to an extra CH3. So now we can actually identify or analyze a bit the NMR of this molecule, or predict the NMR of this molecule, because we understand the environment, the splicing pattern, and the chemical shift. So first of all, is there a symmetry? No. Is there, how many peaks are we going to have? 3, because none of these hydrogens have similar neighbors, because this CH2, yes, it has a CH3 attached, but this is, no, actually, no, there is nothing similar about it. I was trying to say something, but no. So we're going to have 3 peaks. Now we know where those peaks are going to be. Those 2, probably this will be the one that is the most shifted downfield, so the further away. Yeah, let's put it in order compared to TMS. This one, this CH2, it has a CH3 group and a carbon double bond, which means that maybe it's the one that it's most affected by their environment. So it's probably going to be the one that is shifted the most. So it's probably going to be here. Then we have one, this CH3, that it's attached to the carbonyl further away compared to that CH3, which means that it's going to be a bit closer, maybe not so much. Probably it's quite similar in position to that other one. But this CH3, as you can see, is now 2 bonds away from the carbonyl, so it's going to be a lot more closer to the TMS. So that tells us the position. Neighbors, we always apply to the n+1 rule. Well, it's 2 neighbors, which means that it's going to be a triplet because of this n+1 rule. So this will be over here and it will look like a triplet. This one, this carbonyl doesn't contribute any splitting because there is no coupling with any other hydrogens because there's no hydrogen. So it's only affected by that CH3. According to the neighbor +1 rule, it's split into a quartet. Okay, so it's going to be 1. Actually, it's a bit further over. Let's put it there. The other one, it doesn't have any neighbors. So if it doesn't have any neighbor, it's still n+1, so it's called a singlet. I wrote it horribly, but it's just a singlet because it doesn't have any neighbors, n+1 rule. So it's really useful to practice and to confirm that you fully understand the 4 things that we need to interpret of the NMR. It's useful to get a molecule and predict the NMR. Then we can do the opposite to fully analyze, which would be what we will do in the exam papers to get a full NMR. And what we want to do is identify the molecule. Obviously, we need to have a bit more information like the molecular formula, but then everything else we could work it out. The infrared is useful too, just in case we have peaks in a similar area and we can't distinguish exactly the functional group. Yeah, but we will need other information as well. But this is, I think, it's a really, really useful practice to understand all of this, the things that we need to consider for the NMR. The only last thing is the integration, and the integration is the number of carbons that make up that group. And normally we write it something like this because it's kind of the symbol. Doesn't matter how we get to that, but it's the area under the peak. And this first one, it would be 2 because 2 hydrogen make it up. This peak that is number 2, 3 hydrogens, so it would be 3. And this one would be also 3 because there are 3 hydrogens that make up that peak. And we can get it as a ratio in terms of size of a ratio of size of 2 to 3 to 3. We could get it like this, or we could get it as a fraction, just as long as we understand that the ratio and this relationship of like 2 to 3. And we're talking about the number of hydrogen that make up this peak. So those are the key things that we get from the NMR: peaks, chemical shift, splitting pattern, integration. The first step would be to get a molecule and work out the NMR of that molecule. And then it would be doing the opposite, full analysis of an NMR. Okay, so I think we could do some examples now. So this could be a really interesting way to basically apply what I just said, getting the molecule, understanding the structure, and then analyzing those 4 things. One thing that I didn't mention is that there are tables that tells us the position of the signals, okay, because they are, of course, known. And there is always a range because it always depends on the environment, but we can identify the position of the signal by looking at tables of NMR chemical shifts. Okay, but otherwise we can always talk about the relative position of the peaks. So the closer it is to an electronegative atom, the further away it will be. Okay, but this is a useful one to practice what I said and to get really, really confident with the NMR. So even though, for example, we do ethyl epropanoate, here's the structure. Yes, we have the group CH2, CH3 on both sides, but always, and we need to get used to do that as a habit, to don't get it wrong, to always look at the neighbors. So this CH3 as a neighbor of CH2 and a carbonyl. We can stop maybe 2-3 bonds after. But this is CH3 as a neighbor of CH2, yes, the same, but then it doesn't have a carbonyl. It has directly the oxygen. And this tells us that actually they're going to be chemically different. And also because this is closer to an electronegative atom, as you can see, just 2 bonds away, but this is 1, 2, 3 bonds away to the electronegative atom. But that's why it's not only looking at the symmetry, which could be easy to misinterpret, but looking exactly at the neighbor. So we know that those two CH3 are going to be different peaks. Then those two, the CH2, what neighbors do they have? Yes, they both have CH3, but one has a carbonyl and the other one is directly attached to the oxygen. So these neighbors are different, which means that each of these hydrogen would be a different chemical environment. So we will have 1, 2, 3, 4. 4 signals. Okay. Relative intensity of the peak. Relative intensity of the signal is the integration. So how many carbons are, how many hydrogens are responsible for that peak? Well, let's call it 1, 2, 3, 4. We would have this first peak is 3 hydrogens. Second peak is 2 hydrogens. Third would be 2. And then it would be another 3. So the relative intensity is that we have 3 hydrogens, 2 hydrogens, 2 and 3. Splitting pattern, we need to analyze the neighbors. So the splitting pattern, we need to remember, of course, what they mean. So T for triplet, S for singlet, Q for quartet, D would be like doublet. But yeah, we just look at the neighbor and then remember that N plus 1. And we will have, that's what we will have. Signal that is an intensity of 3 and it looks like a triplet. Then we have 2 quartets and then another triplet. But the order, we need to think about that. So the position of the signal. To get the values, we will look at some tables that are probably provided that actually are going to be provided on the sheet of an exam, or we can just find it in the book. But let's think about the relative position of them. Which one will come first and which will come last? So we need to think which one is the closest to the electronegative atom. It's going to be the one that is the far away. So we see the number 3 is directly attached to an oxygen. So that's for sure is going to be the one that is the most shifted. So let's say that 3, it will be the one, let's say, most shifted. Let's say here it's downfield and here is upfield. So closer to the 0 of TMS, yep. If this is just relative. 3 will be the one that it's most far away because it's next to the electronegative atom. Then we have this group number 2 that is attached to a carbonyl. So that's probably going to be quite far away as well. And then what do you think? 4 or 1 will come first? I would say number 4 is further away, even though they're similar neighbors, but just 1 it's 1 bond less attached to the electronegative atom. So probably will be number 4 here, number 1 here, probably still close. And we will see they're going to be within the same range, but 1 maybe would be a bit closer to one range and the other one closer to the other. Yeah, so the position, I think, is all relative, yeah, in terms of the neighbors. Yeah, but this is the type of analysis to do and could be good to do also the other examples.